Hi everyone, I'm Kaylee and today I'm going to be talking to you about muscle adhesion. And I'm actually going to be using a few papers to do this and I'll reference them throughout. The first one is going to be Weight in 2017. All right, so let's jump right in. This purple thing is our muscle shell. And inside of there's this squishy little animal and it has a fun little appendage that can come out. That's called a foot. I'll highlight it here in yellow. We can think of this foot as kind of an adhesive making factory. It generates all of these little structures that are sticky little pads of glue, you can think of them as. They're called plaques. And then these long, tough strings that are called threads that attach the muscle shell to the surface when things like waves or predators come along. And so let's dive into what this foot actually looks like. So let's actually draw out our system pretty in depth. So our box is like the whole system, and then we have this surface down at the bottom. And so the foot forms an interface with this surface. It's got this like suction cup looking structure here, and then it extends up and into the squishy body of the animal. And on the outside, we have seawater, which we know is salty and has a pH of about 8. And so in order to generate the adhesive plaques that stick it to the rock, this foot goes through a bunch of different changes. And I'll walk you through those series of steps. So the first one is instead of the whole foot forming an interface with the surface, it suctions up in the middle to create this isolated chamber. And you can think of it as like a little reaction chamber. And so it can change the environment in that chamber to be different than this external environment of the seawater. And the first thing it does in doing that is adjust the pH. So we add a bunch of protons and we get a pH of about 3. And then it also generates a reducing environment. So it secretes a lot of this reducing agent called muscle foot protein 6 because it does not want oxidation to happen. And then the third thing that it does is secretes these adhesive proteins called MFP3 and MFP5. I'll write it here just so I remember. And then it goes through these really cool fluid changes, which I definitely encourage you to look up, but I don't have time to talk about. And that allows it to kind of create this sticky plaque that I'll make red. And then that interfaces with the surface. And then it generates this kind of skin over the top of it and the thread that you see up here in the mature structure. Now, after all of that, the foot can kind of pop off. So that's gone. And then the foot goes on to make the next structure, say over here or over here. So that gives you kind of some background of what's going on. But then we want to know, how do these proteins actually create that high adhesive strength that we're interested in? So they're actually really rich in this molecule on their side chains that is called DOPA. And it looks something like this with 2 open hydrogens that are really ideal for hydrogen bonding with the surface below. So these 2 hydrogens form hydrogen bonds. This is called bidentate hydrogen bonding because there is 2 of them. And so scientists are really interested in replicating this unique chemistry. And we can actually see why if we determine the bond strength of these individual hydrogen bonds, which is something that Danner et al. Did in 2012. So let's look at the bond strength. So in that paper, they were using a surface force apparatus. And they basically had 2 surfaces, so like one here, one there. And in between them, they were interested in specifically muscle foot protein 5, which is one of those adhesive ones that I was talking about. And they basically just pulled apart these 2 surfaces and determined what that force of adhesion was for the total amount of protein that they had. And then from that value, they could kind of work down from that total adhesion to the amount of adhesion for these individual hydrogen bonds. So the first thing that they did was they needed to know the volume of protein that they had in this little layer here. And to do that, they measured the surface area that they had of the protein deposition, the thickness, and then the volume fraction of protein, because not all of that little coating of stuff is actually the protein. So we want to make sure we get the correct amount for our volume calculation. Then they were able to get the mass of protein by converting using the density, which is a known value. And then through some fancy techniques, which we're not actually going to go through, they were able to determine how much of that protein is actually at the interface rather than at the bulk. So they did some calculations to be able to say the mass at the interface of the protein. And then using that value, we can do some fun chemistry conversions. So we have grams per meter squared of the protein. We can convert from mass of the protein to moles of the protein. And then from moles of the protein, we actually know the ratio of protein or of DOPA molecules that we have in the protein. So we end up with moles per unit area of the DOPA molecule. That's when we can go back to this total adhesion force. And now that we know how many DOPA molecules are contributing to that total adhesion force, if we divide, then we should be able to tell the amount of adhesion that each, meters squared here. The amount of adhesion that each DOPA molecule contributes. So then we divide by our moles, meters squared of DOPA. That 2 is really bad, I'm so sorry. So that gives us the force of adhesion per DOPA in kilojoules per mole. And then if we look back up here, we know that one DOPA molecule has 2 hydrogen bonds. So if we divide, moving all around, if we divide that by 2 H bonds, then we can get the force of adhesion per hydrogen bond. And this study actually found that that is between 18 and 20 kilojoules per mole. So that's pretty good, but that is highly dependent on the conditions that that are in this reaction chamber that we talked about up here. So DOPA is a molecule that is very easily oxidized. And when it gets oxidized, it is not a functional adhesive. So if this is our molecule and say we have some oxygen present, that oxygen is going to steal these 2 hydrogens off and form a water molecule through this reaction right here. So if you remember your redox chemistry, this is going to end up no longer having these hydrogens to form a hydrogen bond. And instead we get dopaquinone, which is going to look something like this. That's obviously not ideal because the muscle really wants to have that molecule to adhere in order to carry out its function. And so what it does is produces muscle foot protein 6, which is a reducing agent. And so it can actually carry out this reverse reaction by changing some of its own bonds. And then we get our functional DOPA molecule back in order to continue to adhere. So that's all kind of the composition of this plaque structure that allows the adherence to occur. But what about the actual structural mechanics of the design of that plaque attached to the thread? Well, we can dive into that too with a different paper from Desmond in 2015. And so they actually wanted to look at like the overall structure that allows this, this to work for adhesion. And so instead of kind of using that surface force apparatus to pull different surfaces apart, they applied a force here, and then they were looking at the peel strength. So the peel strength is represented by force of adhesion over this constant value here. And so in order to do this, they needed to treat this plaque right here as a thin extensible film. And in doing so, they can use this equation. So peel strength equals GC, which is fracture energy, over 1 minus cosine theta. And fracture energy is actually the energy per unit area that is required to separate that plaque from the interface. And so with this equation, there's a few things to note. We can see that if we increase the angle, we're going to decrease the peel strength. And so Mussel's actually arranged these structures to have angles between 5 and 45 degrees radiating out from their shell. And so they've actually been able to optimize the peel strength in this way. The other thing that is really cool that this study found is that the overall fracture energy of the entire plaque is much, much greater than the sum of individual fracture energies for the adhesive proteins. That is not how you spell individual. So sorry. Individual proteins. And so what that tells us is that the structure, the supramolecular structure, is actually enhancing the adhesion alongside that composition that we were discussing before. In other words, composition and structural mechanics are both required for the adhesive properties that the muscle needs to carry out its function. And so as engineers, when we want to apply this to different functions like biomedical or industrial applications, we want to learn lessons both about that composition and the structural design in order to obtain those same impressive properties. And I'm going to encourage you all to look up some of the applications that are currently being investigated and maybe share them in the comments.